So we're doing the 1993 mechanics test, multiple choice number 32. And here we go. Oh, I need to pull this down a little bit so you see the picture. So it says we've got a satellite in an elliptical orbit around a planet P. So here's the great planet P. All right, as shown in above, with R1 and R2 being its closest and farthest distances, respectively, from the center of the planet. If the satellite has a speed of v1 at its closest distance, what is the speed at its furthest distance? Now, here's the thing you need to understand about orbits, elliptical orbits. It's all about angular momentum. That angular momentum is conserved when an object is in orbit around another object. So that the angular momentum of 1 is going to be equal to the angular momentum at location 2. Well, what is the angular momentum? Well, remember, angular momentum is R cross P. So R1, P, where P is the linear momentum. Okay, now I'm going to simplify this. This is just R. And what is P? It's M times V. Now, sine of theta, right, or sine phi, right, it's a cross product. But look, and this is on the multiple choice. They will always do this. They'll always have you deal with this part here and this part here. Why? Because the velocity here is perpendicular to R1. The velocity here is perpendicular to R2. So the sine of 90 degrees is 1, so you don't have to worry about the cross product. Basically, it's your maximum, it's going to be the sine of 90 degrees, so it's equal to 1. So the cross product is just going to be R1, M, V1, and that's going to be equal to R2, M, V2. So the mass of my satellite doesn't matter, as you would expect. What is the speed at its furthest distance? So we want V2. So V2 is going to be equal to R1 over R2 times V1, which is A. So the correct answer is A. Is that right? Is it A? Is anybody? Hello? Hello? Anybody?
Yes, it's A.
Anybody?
It's A.
Okay. Yeah, 32 is A. Okay, I feel like I'm in Ferris Bueller's classroom sometimes. Okay. Oh, I'm off camp. I'm off campus. I'm off camera. All right, so this is A. That is all. Oh, wait. Now, look. So you're doing this you're doing your corrections. What's the big idea?
L1 equals L2.
L1 equals L2 for what?
Conserved in a planet or in a satellite.
For orbits. Okay? And another big idea. What is L?
R cross P.
It's R cross, yeah, and or I'll just go MV, it doesn't matter. And what else do you need to know? Well, how to deal with the cross product here, but that's okay, that's implied there. Make sure you, now, one last thing for this problem, take a look. Why is angular momentum conserved? Let's take a look at an elliptical orbit. This is a good review kind of thing here. Here's an elliptical orbit. Could be a circular orbit too, doesn't matter. So here's our star, and here's our planet. Let's look at it some other place. And look at the force. Here is the force of gravity applied to the satellite. Okay, and it's a central force. That is, this force is pointing towards the center, towards the star. Now, what is R? R from the star to the satellite looks like this. Now, how much torque is applied to this star? Well, torque equals R cross F So this is R. And then this is the force of gravity. I'll just put F sub G. And then because it's a cross product, you go the sine of the angle between R and the force of gravity. But that's going to be always, everywhere, 180 degrees. And what's the sine of 180 degrees? 0. In other words, if you've got a central force pulling a planet or a satellite around something, whether it's an elliptical orbit or a circular orbit, doesn't matter, gravity is not applying any torque. And therefore, angular momentum is conserved. Remember, another way of saying torque is the rate of change of angular momentum, if you have a net torque. Well, if this is equal to 0, if the torque is equal to 0, well, then your L is a constant. Your angular momentum is constant. Okay? So this whole chain of logic that I've explained to you, they'll probably use it in other problems as well. So it's good stuff to know. All right. I think I need to quit now. That is all.